Hi everyone, welcome to this video. So in this video, we will start discussing about the next time complexity, that is linear time space. In the previous video, we discussed about the constant time complexity in which our number of operations were independent upon the data size. But what we will see here in this example, in this particular scenario, is that as the size of my data set increases, the number of operations or the time required to execute the code, it keeps on increasing. And there are multiple levels of increase, which so for example, there can be a linear, there can be quadratic, there can be exponential, they can be logarithmic. So we will discuss all of them. In this video, we are going to discuss only the linear time space. So let's start with the two examples that we discussed in the previous video. But first of all, if you remember, we discussed the contact book example. Now let us have that thing once again. Let us have open your phone once again and have it in your hands. So, and open the contact list. So let's say this is your phone once again, and this is your search bar at the top. Okay. So let's say the search bar looks something like this. And let's say you have multiple various names present in your phone. Okay. So let's say row by row, there are different contacts present in your phone. In the previous video, we discussed that if you have to find a person by name, for example, if you have to find the contact number of a person by name. Now in this video, what we are going to do is that the question that we have now, that you have this phone in your hand. Now the question that you have in front of you is how many people, or you can say that how many people in this particular list have their name starting with A, for example. Okay. So what I mean here is that let's say there are, for example, let us say there are 1000 contacts in your phone, right? And let's say 1500 and 2000, three scenarios let's take. So how many people they have their names starting with A? Okay. So how will you do this particular question? In the previous one, you just search. In the previous video, we just wanted to search a person by name Durgesh Mehta, and we just put him in the search and we got him. In this particular question, we are asked how many people have their name starting with A. So what you will be doing, you cannot search it directly here, right? I mean, you can do one thing, you can just simply put an A, but you will have to, for example, you will have to scroll through all those particular list. Okay, let us say those classifications are not given, or for example, this search tool is not there. How will you do this particular scenario? So in this particular case, what you will have to do, for example, let's say it starts with A and ends with Z. For example, let's say this is the complete scenario. You have to find the names of this particular type, where name is starting with A and finishing with Z. Now there is no set formula for this which you can put in your search box and you will get the example. So what you will have to do, you will have to scan through each of the contact one by one and check, does this match this pattern? If it matches, yes. If it does not match, you will say no. Okay. And similarly you will do for all 1000, and then you will just see how many people have their flag marked as yes. So for example, let's say here you did for example, you got for 500 people, here you got for 700, here you got for 800 people, correct? So what are you exactly doing in this particular case is you are scanning each of the contact one by one, correct? And you are moving. So for example, when you had only 1000 contacts, how many searches you did? You did 1000 searches. When you had 1500 contacts, you did 1500 searches. And when you had 2000 contacts, you did 2000 searches. Okay. So to solve this particular question, the number of operations that you are doing is increasing with the number of contacts in your phone, correct? And this is called linear time space. So for example, to let's say, let me remove this particular few things. So let's say, let's clear few things here. Okay, so let me clear this part. So we are searching with A, Z, these kind of names we are searching. Now what is happening right now? So let's say you search. Now for example, to search one particular name, it takes you 1 second. Okay. Now to answer this question for a data set with 1000 contact, it will take you 1000 seconds. Correct. And for data set with 1500 rows, it will take you 1500 seconds. And for something with 2000, it will take you 2000 seconds. So you see that the time of execution of your code is increasing with the data size, and this is called linear time space. Why linear? We will discuss it while plotting with a graph basically. So let me show you why is it called linear. This is called linear because let's plot this particular graph here where you have size of the data set. Okay, let's say this is the size of your contact list, size of your contact list, and number of second, or for example, let's say this is time and or number of operations. And what we discussed, for to search one thing, one contact, it takes you one operation, or you can say 1 second. Now when you had only 1000 contacts, how much time did it take? It took you 1000 seconds. Okay, now if you have to plot this particular point, it will come out to be here. Now for example, let's say your contacts increased, it increased to 1500. Now for 1500, it will take you 1500 seconds or operations. So the next point will come to be here. Similarly, this if you plot this, it will look like this. And if you curve this, if you create this particular line, it comes out to be a linear straight line, and that is why this is called a linear time space. Okay, so the number of operations, it varies linearly with your size of data set. So we will try to understand this with one more example. Let's discuss the same example, the bookshelf example. So what we had this particular bookshelf which was present here, and it had 500 books here in the first part. Okay, so it had 500 books. And what happens is that every day 10 books keep on increasing. So you keep on increasing 10 books every day. So day 1, for example, it will be 10, 10, 10. This partition keeps on adding, okay, indefinitely. So now your question is, the question that is asked to you is, how many horror books are there? How many horror books are present on shelf? Are present on shelf. So how will you do this? To solve this particular question, it's pretty simple. You will start from here, particular search, you'll start from here. You'll check the first book. Is it horror or not? Okay, so let's say book 1. Again, you'll check. If it is horror, then you will say yes. Otherwise, you will say no. Now book 2, you will check, is it horror or not? Let's say it is no. Okay. Similarly, you will keep on searching till book 500. Let's say now you come with book 500. And let's say it comes out to be yes, horror. Now you will count all the number of yes in presently, and it will give you number of books. So what did you do here? You scanned each of the book again one by one. And this is called linear time space, where you have to scan the whole data set, correct? And starting going one by one. Now, as for example, let's say today is 1st of October. Now tomorrow there will be 510 books. So for today, how many operations required? Today for 500 books, 500 operations required. Now tomorrow there will be 510 books. So 510 operations will be required. Okay, and similarly, for example, 600 books, so 600 operations will be required. So what is happening, that your number of operations or number of your scans is increasing with the number of books that are present in shelf, and hence this is called a linear time space. I hope now you understand this. Now, for example, let's say if I try to plot this particular part as well on the chart which we just saw. So let's see here. So let us say this is the number of operations, and this is the number shelf size. This is your bookshelf size, and this is your operations. So what was happening when you had 500 books, you had 500 operations. Okay, so this is 500. So this is 500 and this is 500. So you will simply match it here. Okay, and let's say this was this particular point. Now when you have 1000, what will happen? It will have 1000. So again it will come to be like this. So here you have 1000 books and it will be 1000 operations. So as your bookshelf is increasing, the number of operations, if you plot, it comes out to be linear. And this is O(n). N means it is dependent, it is only dependent upon n, not to the any power. Okay, so this is called linear time space. Now so here what we are doing, for example, this is a list present or anything 10, 20, 30, 40, 50. Here we are executing, we are searching each of the element one by one. First we go to this, and we have to scan whole of the list, whole of the data structure, whatever we are using. So I hope this explanation is clear. Now let's move towards the coding part of it. So let us see this linear time complexity with few, like we will try to solve 3 to 4 Python coding questions. So even if you don't know Python coding in depth, it's fine. We will be, as I mentioned, we'll be solving the Python coding questions in later sessions. This is just to show you what type of code we do and what type of time complexity it is. So let us say the question 1 that we have, for example, you have a list. Okay, you have to search for a particular element in list and return its index. Okay, so what do we need to do? We have a list, for example, for example, list is 100, 110, 120, 130, 140 and 150. We have to search up for a particular target. Let's say the target is 120. Now my goal is to search for this number in this particular list and return its index. So what I will do, simply for a in list and for I in, or it could be like for I in range of list. Okay, now what is happening? It will range of length of list, So it will check across the length of the list. If list of I is equal to my target, so I have to declare something, let's say print, and you will say f string the index of the target number, and we'll print, we'll see, simply say target is, and we will return I here. Okay, in this particular scenario. So what we are doing here, we are checking if we find any element, we will return the index of the target number, this is this, and if we don't find, we will simply print could not find the number. So this is it. And now once we run it, so see what is happening. Now why I showed you print here is that it is executing for each of the number. If you see here, first of all, the pointer will go, this I pointer will go to this element. It will check, does it contain the target? No, it does not match with 120. So it will print this particular statement. Okay, and for example, then it will go to 110. Then it will say no, it could not find the number. The index of the target for the third element, it will find the match, so it will return the index. And that's how it works. That's why I have created this print statement, to show you the number of operations involved is 1, 2, 3, 4, 5, 6. It is exactly same as the length of this particular list. So what is happening? We are going one element. Now, as the size of your data set increases, for example, you see 160, 170, and 180, 190. So what happened? You increase the size of your list. Now, once you do this, you will see the number of operations getting increased. So this is what it means, that as the length of your data set increases, the number of operations increase. Now let's try to solve another question. For example, you have a string here. So let us say you have a string, let's say text is equal to hello world, my name is Jadoo. Okay, let's say this is the text, and you want to see if a particular character which is equal to, you can say O, or the count of a particular character does, for example, you want to check how many times is O occurring in this whole particular text. You want a count of that. So how will we do that? We will simply take a count equal to 0 initially. Okay, then we'll do for A in text. Okay, for A in text, if A is equal to char, which is my this, count is equal to count plus 1. Okay, if A is equal to this, and then simply print count. So what we are doing here, we are simply checking, we are initializing count with 0, and then we are doing with see, for if you're getting confused again with the code, don't worry, I'll explain all these codes with proper visual explanations as I have done earlier as well. But right now my objective is not to show you Python coding. It is just to show you the number of operations, how do they increase with the increase in text. Okay, so just focus on that part. Now let's say I run this particular code. So I see O is occurring 4 times. So let's see, O is 1, 2, 3 and 4. So 4 times is occurring. Now for example, let's say the length of my text increases. Okay, we are waiting for you since 2010. Okay, now what happened? We increase the text here, and if you see what will happen, the count will increase. So how this code will exactly work is that it will check each of the character 1. It will go to character 1. It will check, is it O? If it is O, it will add to this, and it will add a count to 1. Okay, and if it is not, it will keep the count same. So it will scan whole of the text. Now if the text keeps on increasing, the number of operations will keep on increasing, and this is the reason why this is called a linear time space. I hope you understand. Now let's look at one final example. Let's say this is the list equal to, for example, 1, 1, 1, 2, 2, 3, 4, 5, 2, 2, 2. Okay, you want to find how many times is 2 occurring. So how do we do that? Let's say P is equal to list dot count, and we say 2, and then we say print P. So what do you see? That here, how this count function works, it goes to each of the element one by one, and it checks. If it is 2, it will count itself, otherwise it will skip. So it depends upon the size. The answer to this particular question depends upon the size of this particular list, and this is what the time complexity is. It is called a linear time space. So I hope you were able to understand this particular scenario. I have attached this particular Python book where there are few questions. You can solve them or you can look at them. Don't if you are skipping Python coding right now, it is totally fine with me, but just understand that why I'm saying that the number of operations will increase with the list size. Okay, so whenever you code, so far we have discussed constant time space and we have discussed linear time space. So whenever you code or you are solving any example, just try to see that does the number of operation of my code have an impact on the number of operations, that for example number of the size of the data set, does this has any impact on the number of operations that I'm doing. Now let's try to create this chart at once at the final. So remember, we created a chart for linear constant time space and linear time space. So how to plot this particular thing? So you saw that, so on the x-axis it is the data set size. Okay, you can say data set size, and on the y-axis you are having number of operations. So how does this chart look for a linear time space? For a linear time space, or ON, it will look like this, as we discussed, ON. And how does it look? So for example, if the data set size is 0, operations is 0. If the data set size is 10,000, it will number of operations is 10,000. Now how does it look for O1? For O1, the number of operation will remain fixed. It could be 1, 2, 5 depending upon your code, and it will remain same irrespective of your data set size. Okay, so even for a 0 size data set, number of operations are same. For 10,000 it is same, for 5,000 it is same, for infinite it is same, and this is called O1. We have seen this graph earlier as well, but I just wanted to show you. Now in the coming videos we will explore few other time complexities as well, and we will see. So the point is, the closer you are to the x-axis, the better the time complexity is. For example, let's say I create a curve like this. Okay, let's say I create an arrow like this. As you along this curve, as you move here, your time complexity worsens, correct? So right now it is O1. Now you reached here, this is ON. Here time complexity is dependent upon your dataset size linearly. But once you go beyond these points, you will see time complexity like n square, n cube, or exponential 2 raised to the power n, and those kind of things you will see. And those are worst time complexities. And now it depends upon your question. So every question that you solve in Python coding, it can have multiple time complexity. You have to see what is the best possible scenario. So so what is the best possible time complexity for this? By best, I mean in the worst case, can I solve this question? So for example, it's a particular question can be solved using ON as well and O1 as well. So what you will prefer to have, you'll prefer to solve it using O1 because this is reducing my time space. So we will discuss all these in detail once I have explained all these particular time complexities. But I hope you are able to understand the constant time space and the linear time space. So in the next video, we will discuss the remaining of the time complexities like log n and log n, exponential, prime, and polynomial time complexities. We will discuss them. So thanks for watching this video. I hope you liked the video. Comment below if you don't understand anything, or let me know the feedback of the video if it is good, and please subscribe to our channel. I will see you in the next video.